I'm ready to get to this weekend here. How about you guys? This has felt like a long week. So, yous guys, I think last time we met you had worked on the homework 3, right? So today we'll start with questions from homeworks. I mean, I guess if you have things older than homework 3, you could ask about those too, but I feel like we hit homework 1 and 2 pretty hard the other day. Although if you still have questions about stuff, that's cool too. Absolutely, go for it, my dude. All right. Yeah, let's do it. You guys got questions from homework anything, I guess? Sure, no prompts. Got a case of the yawnies.
You know, yawns are contagious.
Yeah.
Oh.
Can we do number 7 on homework 3, please?
Number 7? Sure. So I'm going to start just by looking at the prime factorizations here. So 24 is 2 squared times 7.
Wait, what? Oh, wait.
98 is 2 times 7 squared. 18 is 3 squared times 2. 50 is 2 times 5 squared. And 8 is 2 to the third. And what I notice here about the piece at the beginning is, yes, there's reducing that I could do, but if I reduce the 2 from the bottom, it's going to ruin the 2 squared. And if I reduce the 7s, it's going to ruin the 7 squared down there. So I don't think I actually want to do any of the reducing. I think I'm probably going to be better off just treating this as a actually, I take that back. Let's do only the 2. And that is going to allow me to get rid of any radicals in my denominator. That might be the easiest way to do that. So what I'm going to have then is 2 times 7 over 7, and then a 3 square root 2, and a 5 square root 2. And over here, this 2 to the third, I'm going to think about as a 2 squared and a 2 to the first. So I have something like that. Does that feel okay so far? Now the 3 square root 2 and 5 square root 2 are like, so I can add those together. So I'm just going to think about that as 8 square root 2. Everybody good there? So we'll multiply these together next. That's going to be 8 And then I'm going to have 2 squared 7 under the square root all over 7. So far, so good, Ben?
Yeah.
I got that 2 squared under the radical. That can come out. And then the 2 times 8 can just be 16. And I think that's really as good as we can get. Notice that the radicals and the 2 things that are left are not like radicals, so I can't do the subtraction. So, I mean, you could make a common denominator, I guess, if you wanted to. Wouldn't be wrong. But I don't really think it's making anything any better for us, so I would stop here if it were me. But if you wanted to call that 16 root 7 minus 42 root 2 all over 7, that's okay too. You know, not wrong. Does that feel all right, Benj?
Yeah. Feels better.
Yeah. There's, again, I wanted to get some places where, you know, like the radicals weren't the same and there's just not anything to, you know, where you couldn't do all the adding or subtracting, just to kind of, you know, point out that that doesn't always happen. Hal's? 3?
Yeah.
Sure. So I'm going to start with a prime factorization. So that's going to be, oops, 2 to the 3rd, and then 3 squared. And that one is going to be 2 squared, and then 3 to the 3rd. Okay with that so far? Now, certainly you could do a bunch of reducing here, right? Like I can do that, get rid of all the 2's. And now it would be tempting to get rid of all the 3's here, right? You can cross out the 2 3's from the numerator and all but one of the 3's from the denominator. And it's okay if you wanted to do that. I would not go that far. I would do this and just reduce one of the 3's, because I want to leave that perfect square in the denominator so that I don't have to rationalize my denominator later on. Although if you did go the rationalize your denominator route, it'd be fine. You'll end up at the same spot. But that's just me being sneaky. Is that okay, Hallie? And again, if you reduced all the 3's, or reduced the 3's completely there, that would be okay. You just end up having to rationalize your denominator at the end, and you'll end up back at the same spot, where you'd end up with root 2 over root 3, and then when you rationalize, you're ending up with root 6 over 3.
Okay.
I just saved the step by not fully reducing the 3's. You know what I mean?
Mm-hmm.
Megs?
So I got 3 over 2. Would that be like a product of reducing?
You got 3 over 2?
Yes.
I don't think that could have happened.
Because I think I asked you about this one in class.
Did we possibly write down the prime factorizations in the wrong order? Did we put the 108 on top and the 72 on the bottom somehow when we were writing it down, and we just goofed something up?
I don't.
Maybe. We can take a look at it here in a few minutes. This sounds like I just need to look at your work and give you some specific feedback kind of question, which is totally fine, and I'm happy to do that kind of thing. But without being able to look at what you wrote down, it's really hard for me to kind of guess as to what happened. You know what I mean? Joe?
Can I ask a question about homework 2?
Sure.
Okay. Could you go over number 11, please?
Yeah,
Thank you.
sure. Okay, so I'm going to start with some prime factorization. So 324 is 2 squared times 3 to the 4th. (560) is 2 to the 4th times 5 times 7. I'll stick that all under one radical. And I'm going to reduce all of the 2's that I can. Okay with that?
Yep.
And I'm going to notice that 3 to the 4th is like 3 squared twice. So my numerator is just going to be 3 times 3. My denominator is going to be 2. And then I still have that square root 5 times 7 in the bottom.
Okay.
Is that cool?
Yeah, I made a mistake because I accidentally put another 3 in the numerator for whatever reason.
Oh.
I did that. But, it's because I didn't split up the 3 and the 4. Okay, but I understand now. Looks good.
And then, well, we still have a little bit more to do because we have to rationalize the denominator.
Yeah, yep.
So I need another 5 and I need another 7. So when I do that, I got 9 square root 35 over 2 times 5 times 7, or 9 root 35 over 70.
Can we just add the terms, the 5 and the 7 in the beginning, so we don't have to multiply by 2, by the 5, the square root of 5 and square root of 7, or does it make a difference? Or should we do the way we did it?
I am not, can you say it one more time?
So, you see how you have the 2 times the square root of 5 and 7, and then in order to get rid of the square root at the bottom, we have to multiply by the square root of 5 and square root of 7?
Yes.
Oh, wait, never mind. I was going to say, what if we just multiply by the square root of 35, but that wouldn't get rid of the bottom?
Well, it would, because
Would?
35 is still the same thing as 5 times 7.
True. Okay, so
So
you could do it.
you could write it that way, sure.
Okay, all right.
Yep, that would be fine. Woody.
Isn't this the cube root?
Oh my gosh.
That's why I didn't do the 3 to this second.
Okay.
Yo.
Hey, good looks, Woody.
Yeah, thanks.
Yes, sir.
So you can ignore everything I did there.
SMH.
You know, we all make mistakes, guys.
Yeah, I mean, you realize.
Hey, do you guys want to shut up? I wasn't telling him that. I was telling Joe that. So if you want to mind your business, that'd be great. Al. It's a compliment.
See, yeah, that's what I
Can you
would
keep
count.
it down?
All right. So here's a place where I would say that an incomplete reducing could help me out a little bit.
Okay.
So I'm just going to reduce 1, 2 from the numerator and denominator so I can have a perfect cube in the denominator. If I did all the reducing, I lose that perfect cube and then would have to worry about rationalizing that denominator also. So I'm gonna do just that is the only reducing I'm gonna do.
All right.
And then I'm gonna think about 3 to the 4th as 3 to the 3rd and 3 to the 1st. So I can take a 3 out of my numerator, and I'm left with a 2 times 3. And I can take a 2 out of my denominator, and I'm left with 5 times 7. Now we'll rationalize. So I need to get rid of the 5 and 7 inside the cube root. I need 2 more 5s and 2 more 7s, right? So I'll multiply by cube root 5 squared and cube root 7 squared. Is that okay?
Yep.
All right, so I have 3 cube root 2 times 3 times 5 squared times 7 squared over 2 times 5 times 7. So I'm going to have 3 cube root 7,350, yikes, over 70. My apologies for goofing that up. I missed. You see how easy it is, though, to like get stuck doing the wrong thing there. Happened to me. You know, we all make mistakes, though. And do it on purpose, guys. Accidents happen, right?
That's how my system's born.
Jesus.
God, that was good.
It's too much information. All right. Any other questions on homeworks? Megan?
Could you do 13 on homework 3?
13 on homework 3. Okay. So I'm going to just start with some prime factorizations. And this time I'm not going to forget the cube root. So far, so good, Megan? So this 2 to the 5th I'm going to think about as 2 to the 3rd and 2 squared. And this 3 to the 4th I'm going to think about as 3 to the 3rd and then 3 to the 1st. So when I reduce my radical, in the denominator, I'm going to have a 2 out front, and then a cube root 2 squared. And in the other one, in the denominator, I'm going to have a 3, and then a cube root 3 to the 1st. So far, so good. Now I need to rationalize my denominators here. So I have cube root of 2 squared. To get rid of that, I need one more 2, so I'll multiply the top and bottom by cube root 2. And in the next fraction, I have cube root of 3, so I need to get 3 3's in there, so I need 2 more 3's, so I'll multiply the top and bottom by cube root 3 squared. So if I do that, I'm going to have 5 cube root 3 squared times 2 over 2 times cube root 2 cubed, and then minus 3 cube root 3 squared times 2 over 3 cube root 3 cubed. So cube root of 2 cubed is just 2, and cube root of 3 cubed is just 3. So I have 5 cube root of 18 over 4 minus 3 cube root 18 over 9. So I do have the same cube root, right? I have cube root 18 in each one of these, so I can subtract them. But to subtract them, I need a common denominator. The common denominator between 4 and 9 is going to be 36. I'll multiply the first fraction by 9 over 9 and the second fraction by 4 over 4. So that's going to give me 5 cube root 18 minus 12 cube root 18 all over 36. 45 minus 12 is 33 cube roots of 18 over 36. And then 33 and 33 over 36 can reduce. So if I divide both by 3, I have 11 over 12. So I have 11 cube roots of 18 over 12. Joe?
So for when you took the cube root of 18 when doing the subtraction, did you choose 18 because it's a larger number?
Well, that's just what 3 squared times 2 was.
Oh,
So
okay.
I just simplified from before.
And then, so when it's minus 12, is it times the cube root of 14? Or is
Oh, that's an 18
oh,
there.
that's 18? Oh,
Yeah.
that's what I was confused.
That
Okay.
just got messy. My apologies.
Thank you.
You're welcome. Again, I recognize that my penmanship is not always tip-top. If it's confusing, like, let me know and we'll fix it. Not a big deal. If you were confused by it, someone else was surely confused by it, especially if they have to go back and look at this like a day or two later. You know, might as well fix it now. Megan, are you happy with what happened there?
Yeah.
You don't seem very happy.
I don't know, just a little confusing, but.
There's a lot to do, for sure. Hallie?
Can I go to the bathroom?
Of course. All right, what do you guys say? Ready to move on? Got our questions answered, at least to some extent?
Yeah.
All right. So we're going to deal with multiplying and dividing, unlike radicals. So when I say unlike radicals, I mean we want to be able to do something where we can multiply the square root of 2 by the cube root of 2. So the number under the radical is the same, but the type of radical is different. This is not something we'd address to now, right? If we have the same kind of radical, and I multiply 2 cube roots together, 2 square roots, or 2 whatever roots, we know what to do. But if they're different kinds of radicals like this, we don't have a good idea of how that's gonna work, right? And in fact, if we're adding and subtracting, we can never deal with something like this. But we can for multiplication. But to do that, we kind of need a new definition of what we mean by a radical. So what we'll do is we're going to define a radical as an exponential. So this is like the radical, and this is like the exponential form. This will be super important. You will use that definition throughout all of the homework in section 4, or in this homework 4, that you guys will work on next. So that you'll want to make sure that you have handy. So just to practice using that a little, let's say we want to write these answers in exponential form with examples. So let's say we have the cube root of 2 to the 4th. Let's not say that. Let's say 2 squared. So the number under the radical is the same as the base for our exponential. The exponent under the radical is the same as the numerator in our exponent. And the index for our radical is the denominator in our exponent. And that's it. We just say that's the same as 2 to the 2/3. Say we have, no, that's not what I wanted to do. Sorry, my apologies. I want to go the other, that. Say we have the 4th root of 4. So this one's a little bit different than the previous problem, because you'll notice that 4 is not a prime, right? So I would start by just doing a prime factorization. 2 squared. Everybody okay there? Now I'll apply our definition. So I have 2 to the 2 over 4. And 2 over 4 reduces to just 1/2, which just worth noting that 1/2 is the same thing as or 2 to the 1/2 is the same as the square root of 2.
Do we need to recognize that?
I'm just pointing out to you, right, that the index on a square root is 2, even though we don't write the 2 there.
Okay.
And the exponent is 1 if we don't write anything there.
Okay.
So I'm just kind of pointing something else out. It's not necessary. But when you get a square root, we have to remember that the index there is 2, right? Do you guys feel okay about just kind of taking a radical and writing it in exponential form? Reverse also exponential form and write in radical. So let's say we have 7 to the 3/5. So the denominator in our exponent is the index for our radical. So this is going to be a 5th root. The number under the 7, and the exponent on the 7 is going to be the numerator from our fraction. And 7 to the 3rd, if I go to my calculator, I think is 343. Everybody okay there? Again, not too bad. We're just kind of using this new definition and the same kind of things that we've done before. We have 2 to the 5/4. So again, the denominator of our exponent is the index for our radical. And then 2 is the number under our radical. And the numerator from our exponent is the exponent on the 2. But notice here that the exponent on a radical is bigger than our index. You guys see that? That should tell us that we can reduce this radical. 2 to the 5th is like 2 to the 4th times 2 to the 1st. So I can take a 2 out, and I'm left with 1 still underneath. And there we go.
Oh, that's cool how you can do that.
Is the homework like this, or is there?
There's some homework that's like this, that's just practicing using this. But the power here is when we have a radical, or if we can convert our radical into exponential form, we have a lot more properties available to us so that we can do a lot more algebraically with an exponential than we can with a radical, which will allow us to multiply or divide two unlike radicals. So let's kind of review some of those properties of exponents that we've kind of collected over the course of our mathematics education, because these will be real important tools, again, for doing the homework. So the first one is that if I have a to the n times a to the m, that gives me a to the n plus m. And if you think about that, just to kind of demonstrate why that's true, if I have 2 squared times 2 to the 5th, 2 squared is 2 times 2. 2 to the 3rd is 2 times 2 times 2. That's 5 total 2s, so I'd have 2 to the 5th, which is just 2 plus 3, right? Just kind of demonstrating to you that like these properties that I'm writing down are kind of simple, right? They're things that we've already kind of know intuitively. I'm just collecting it into a really compact form. Our next one is if we have the exponent of a product. So that tells us that we can have the exponent of each of the factors of the product and then multiply together. So like, let's say we have 2 times 3 squared. That's the same thing as 2 times 3, 2 times 3. So I have 2 2s and 2 3s, so 2 squared times 3 squared, and then just kind of demonstrating to why these properties work, and that they're not anything weird. They're things that we've been doing kind of all along, right? We're just kind of compacting these together into a easy to use rule. The next property is if we have an exponent of an exponent. So if we do that, we multiply the exponents. Just to demonstrate why that's true. So if I have 2 squared to the 3rd, that means I have 3 2 squareds, which is 2 times 2, 3 times, for a total of 6 2s.
Oh, so you do the exponents first before you do like 2 to the 2nd. That probably doesn't make any sense to you, but like.
I know what you're saying. Yes, usually you work from the outside in.
Okay.
When dealing with parentheses.
Okay.
Is kind of the standard. But like what I'm doing in red is just demonstrating why this rule is true. You don't actually have to do what I'm doing in red to use the rule.
Yeah.
The shortcut is to eliminate having to do all the nonsense that I'm doing there in red. I'm just kind of demonstrating you that like this isn't magic. This is pretty basic, just based on the definition of what we mean by an exponent. But sometimes it just like, it's nice to see like, okay, sure, that has to be true because, yeah, that's how that would have to work. And, you know, because we're not going to prove anything in a course like this. So I want to give at least some kind of justification for these things. Yes, sir. Yes, sir. Do you Do I want to do that one next? No, I think I want to do this one next. So if I have a to the n divided by a to the m, that's a to the n minus m, which hopefully isn't really surprising, right? When I multiplied two exponentials together, I added their exponents. When I divide two exponentials, I'm subtracting the exponents. So the easy way to think about it is like if I have a to the third over, let's use a number, 2 to the third over 2 squared. And just like 2 times 2 times 2, and then 2 times 2 on bottom. Those cancel out, and I'm left with like 2 to the first. Everybody okay there? Again, just like what we've been doing, we're just kind of formalizing that into like a property. So the next one is if we have the exponent of a fraction. So if I have like 2/3 squared, that's just like 2/3 times 2/3. And when we multiply fractions, we just multiply straight across. So 2 squared over 3 squared. The next one is that anything other than 0 to the 0 power is equal to 1. To see why that's true, if I think about 1, that's the same thing as like 2 over 2, right? And if I use property 4, that would be like 2 to the 1 minus 1. And 1 minus 1 is just 0, right? To kind of show you why anything to the 0 power is the same as 1. Because it's just like dividing that number by itself. Allie?
So how come we don't put a 0 up there? Like, what's the point of it? If it's just like...
I'm sorry, go ahead. Why do you put a 0?
Wait. So if it was like 5 to the 0 power, the whole thing would just be equal to 1, or would it be equal to 5?
1.
Okay, never mind. That makes
Anything to the 0 power other than 0 is 1.
sense. Okay. Yep.
0 to the 0 is undefined.
Okay.
Because you're dividing by 0, basically. Right?
Okay. Yeah, that makes sense.
5 to the 0 means 5 over 5,
Yeah.
which is just 1.
Okay.
Well, negative 0 is just 0. And then our last property here, a to the negative n is equal to 1 over a to the n. So if I have like 2 to the negative 2, negative 2 is the same thing as 0 minus 2, right? And then if I use property 4, that's the same thing as 2 to the 0 over 2 squared, which would just be like 1 over 2 squared. So basically that negative exponent is just creating a reciprocal. So these properties, again, super important. We'll be using those throughout our homework 4. So in addition to that definition, we'll need these properties. Now let's do some actual examples of, other than just using the definition like we did before, let's do some actual multiplication division examples. So let's start with the one that we led off with, that the goal for this lesson was to be able to do stuff like this. So I noticed that the 2's are both primes, so I don't need to worry about doing a prime factorization. And now I'm just going to convert them into exponential form. So the first one, I know the exponent there is a 1, even though it's not written. So that's going to be 2 to the 1/3. And then the square root of 2, the index there is 2, even though it's never written. And the exponent is 1. So that's 2 to the 1/2. So far, so good.
Yep.
So now what I have is a situation like property 1. 2 to the 1/3 times 2 to the 1/2 is going to give me 2 to the 1/3 plus 1/2. Does it help if I write the property over the equal sign for you guys? If you're going back to look at this to know why I did that? I can do that. Everybody's okay, though, with what I did there? So to add 1/3 and 1/2, I need to make a common denominator. The common denominator between 1/3 and 1/2 would be 6. So I'm going to multiply that first fraction by 2 over 2 and the second fraction by 3 over 3. That's 2 to the 2/6 plus 3/6, which is just 2 to the 5/6. Remember, when we add fractions, we add the numerator, but the denominator just stays the same. And then I can convert that back into a radical using our definition. So the denominator of the exponent is my index for my radical. And then I have a 2. And the numerator for my exponent is the exponent under my radical. And then if I type into my calculator 2 to the 5th, that is just 32. So rather surprisingly, the cube root of 2 times the square root of 2 is the 6th root of 32. Probably would not have guessed that, Joe.
So the 2 that was not square rooted at all, like you know, talking about the 2 that you have towards the left, the beginning of the problem, did you end up putting that in the square root after we found the common denominator? You see how you have like 2 equal to 2 equal to 2? You know what I'm talking about?
I have 2 to the 1/3 times 2 to the 1/2 equal 2 to the 1/3 plus 1/2.
Yes, so that 2, did you end up putting it inside of the square root after you found the common denominator?
So there is no 2. This is a number and this is a number, but neither one of those numbers is 2. Right? That'd be saying that like 2 to the 3rd is 2,
right,
and then a 3, and it's no. 2 to the 3rd is the whole number. Like the exponent is part of it.
Okay.
Does that?
That makes sense.
Okay. Because the question you're asking like kind of doesn't make sense.
No, I know.
And you get now why I'm.
Yeah.
Okay.
I'm good.
Okay. So the goal here really is we start in radical form. We convert to exponential form until we have everything combined together into a single exponential, and then you convert it back to radical form, right? So we did all of our simplifying really inside the exponential form, and then got a radical back. Let's do another, or we'll do several here. So let's say we do the square root of 2 divided by the cube root of 2. Okay. So again, there's no prime factorization to do, so I'm just going to go ahead and convert these straight to exponential form. So square root of 2 is 2 to the 1/2, and cube root of 2 is 2 to the 1/3. And now we're going to use property 4 to say that's 2 to the 1/2 minus 1/3. Again, to subtract two fractions, we need a common denominator. That common denominator is still going to be 3. So I'll multiply the first fraction by 3 over 3 and the second fraction by 2 over 2. So that gives me 2 to the 3/6 minus 2/6. When we subtract those, we get 1/6. So far, so good. Okay, that's a single exponential now, so I'll just convert that back to a radical. So the denominator gives me the index, and the numerator tells me my exponent. So that's my answer. Everybody okay there? What's a little bit more complicated is if we had done the opposite, or the reciprocal, I should say, and tried doing the cube root of 2 divided by the cube root of, or the square root of 2. So let's do that one. So again, no prime factorization to do, so I'll just convert these to exponential form. And I'm not going to talk through how to do that because it's been the same exponential form for the last 3 examples, right?
Thank you.
So we'll use property 4 to rewrite that as 2 to the 1/3 minus 1/2. To subtract the fractions, we'll make a common denominator, that common denominator being 6. So the first fraction I'll multiply by 2 over 2, the second fraction by 3 over 3. When I subtract 2/3 and 3/6, I get negative 1/6. I have a negative exponent there, so I'm going to use property 6. That's going to allow me to write that as 1 over 2 to the 1/6. Now I'm going to convert this back into my radical form. And off fiddlesticks. I have a radical in the denominator of my fraction. So we have to rationalize that now. So currently I have the 6th root of 2 to the 1st. How many more 2's do I need under that 6th root to get rid of the radical part?
6.
5 more. I need 6 total. I have 1 already. So we'll multiply the top and bottom by the 6th root of 2 to the 5th. Which is just going to be 2 in the denominator, and 2 to the 5th is 32, so the 6th root of 32 over 2. Now, this is the obvious way to have done this problem, and though it's not the fastest. Let me point something out to you. Oh, Megan, do you want to ask a question first?
Yes. So how did rule 6 apply to that one part?
Oh, maybe it's rule 7. Is 6 the 0 power?
Yeah.
Oh, sorry, I meant 7. Thank you.
You're good.
Good question. Okay. So, for me, what I'm going to do in the beginning, I notice the index of the denominator is bigger than the index of the numerator. You guys see that? So I am going to start this problem by rationalizing the denominator now rather than waiting.
Wait a minute.
And the advantage there is that this is what we did in example A, right? That's the exact problem we had in example A, which I already know the answer to.
So can we do that every time the index in the numerator is higher than the index in the denominator?
I think that that makes it easier to rationalize the denominator first.
Okay.
Although if there's like reducing in the radical to do, I would do that part before I rationalize, but
Okay.
it's a good option to have. They're both going to get you to the right place. One of them is maybe a little bit more time consuming than the other, but not substantially, right? I've just shortcutted through a lot of work because I just stole all the work for part A, that I didn't have to do here because I already did it, that problem. Yes, Megan?
So does that only work out when you've done that problem beforehand?
Well, it's still, I think it's it's easier to rationalize the denominator here than it is later, because rationalizing a square root of 2 versus a sixth root of 2, it's easier to make a mistake with the sixth root of 2 because there's you got to do a 2 to the 5th. So it's usually easier to rationalize the denominator earlier. But yes, I mean, having already done the part of A is what makes it so substantially shorter, but the rationalizing the denominator, I think, is easier to do earlier rather than later. That's assuming, though, that you know that it's coming, right? If you don't know the rationalizing is coming, then, it's not of a lot of help. All right, let's do now the third root of 18 times the fourth root of let's do 24. So here I would start by doing a prime factorization, because I noticed that 18 and 24 are not perfect square, or not prime numbers. 18 is 2 times 3 squared. And 24 is 2 to the third times 3. Again, I'm doing these in my head. If you have to draw your factor tree and use your calculator, totally understandable. Not my expectation you're able to do these in your head. Now I'm going to use my definition to convert these into exponential form. So I'm really kind of thinking about the problem this way. where I have the cube root of the first power of 2 times 3 squared. So it's going to look like that. And similarly, here. Everybody so far so good? So that's just using my definition. Here, this part looks like property 2. And I'm doing that twice, once for each set of the parentheses. Everybody okay with that? Now we have these exponents of an exponent, so I need to use property 3. So there we're going to multiply the exponents. And remember, to multiply two numbers, we multiply the tops together and the bottoms together. So I'm just going to take each of these whole numbers and think about them as over 1. So that gives me 2 to the 1/3 times 3 to the 2/3 times 2 to the 3/4 times 3 to the 1/4. So here is a property 1. And here is a property 1. Everybody's okay to that? Now to add these fractions, we need a common denominator.
12.
12 is the common denominator.
Love to see it.
So I'll multiply the first fraction by 4/4 and the second one by 3/3.
Still.
And when I add those fractions, I get 2 to the 13/12 times 3 to the 11/12.
Love to see it. Wait a minute.
Then we'll convert them back into radicals. So the first one becomes the 12th root of 2 to the 13th. And the second one becomes the 12th root of 3 to the 11th. But notice that the exponent on the 2 is greater than the index for our radical. So that one can reduce. So I can think about that as 2 to the 12th. And then 2 to the 1st. So I can take a 2 out. I have the 12th root of 2 to the 1st times the 12th root of 3 to the 11th. And those are the same radical, so I can just multiply the stuff underneath them together. If I go to my calculator, 2 times 3 to the 11th is
75 million.
354,294.
That's what I was thinking too.
Yeah. Not one that we're probably doing in our head.
Just gotta stay organized for these ones.
Yes. This would still be okay, though, if you just left it with like that and you didn't multiply it out in your calculator. That's okay for me also. Megan.
Oh, I'm not reading it.
Oh, okay. So, that was a lot of writing, though, for one problem, right? That's okay. That's where I want us to be right now, because there's a lot of steps going on here. Eventually, once we get a little bit more comfortable, we'll start showing you guys some shortcuts to shave some of the writing down, just like we did before. Remember, when we started reducing radicals, it was quite a lengthy process, and by the end, I had kind of streamlined it down for us to where it's like, basically, you look at the prime factorizations, and maybe there's another intermediate step, but it's usually, like 2 or 3 pieces of writing, and you're kind of done with it. We'll do the same thing here, but in the beginning, I'm writing out every single little thing and showing all the little transitions, because there's a lot of stuff going on, and you have now exponents that have fractions in them, and it's a lot to kind of keep track of when you're first starting to do this. So I'd encourage you, again, be neat, be organized, go slow, look at the properties, make sure you're using them correctly. But as we go through this, and when we look at the homework again next week, and we do some more practice on this topic, we'll start looking for shortcuts and ways to kind of condense some of the work that we're writing out. But don't be afraid to write a lot here for these ones. So homework 4 is already posted in OneNote. So the first 3 problems, you're just using your definition to convert these into radical form from exponential. And then similarly here, on the next 3, you're converting from radical form to exponential. And then your last, 8 or whatever here, are some problems kind of like what we did in the examples. Now, fair warning, some of these are quite difficult. And there's not a big deal if you don't, if you need to stop partway through, or you get started and you get to so far and you're just like, I don't know what to do anymore, and just take a little break and go on to the next one. That's all fine, right? Do as much as you can. This is difficult, especially for your first time, as we're getting used to doing this. So don't get frustrated. If you can't finish a problem, don't just quit. Just stop where you're at and go on to the next one. Write yourself a note to hey, need to come back and ask a question about this one or whatever. That's okay. That's good. That's part of, how this works, how learning mathematics works, is you get confused by something and then you ask a question and you're like, okay, I know what to do when that kind of thing happens, and you keep moving forward and making a little bit of progress at a time. But we're going to stop here, so give you guys, 15 minutes or whatever to kind of start and try a couple of problems from the homework before we have to go. Okay?